Let's apply the Force Toolkit in some useful examples. So make sure to pause the video and write these steps down. The first thing you need to be able to do when you use the Force Toolkit is identify the system that is being accelerated. Then define the coordinate system. Identify the forces by drawing a force or free body diagram and include a motion map. If necessary, draw a component diagram, and if necessary, rotate the axes. Explicitly write the sum of the forces equals mass times acceleration. Replace the sum of the forces with the actual forces in your free body diagram, and if necessary, write the sum of the forces equals ma in the horizontal and vertical directions. Substitute numeric values where appropriate and solve for unknowns. Okay, in this sample problem, an 85 kilogram person is standing on a bathroom scale in an elevator. We want to know what the person's apparent weight is when the elevator accelerates upward at 2 meters per second squared. So our first step is identify the system being accelerated. And in this case, the system being accelerated is the person. Then we want to identify the coordinate system. So up is positive, down is negative. We want to identify the forces by drawing a force diagram or free body diagram and include a motion map. So this is actually really important in this problem. So let's look at what's happening. It says the elevator is accelerating upward at 2 meters per second squared. So what that means in our motion map is that the velocity is increasing on the way up. So if that's the case, the acceleration has to be upward. Because remember, the acceleration arrows always point in the same direction of the velocity arrows if the velocity arrows are increasing. So if the acceleration arrows are pointing upward, that means for our force diagram, our force pointing upward must be greater than our force pointing downward. Now, a force pointing upward will be the force that the scale is providing onto the person, and our force pointing downward will be the force due to gravity on the person. So once again, like we said, this force, notice that this force, the scale, has a larger force than does a force due to gravity. Now, just to make sure we understand, sometimes this force of the scale can also be called the normal force. So in some problems, if there's no scale, they're just referring to the normal force. Also, this is what is sometimes referred to as the apparent weight. All right. So now we want to explicitly write F is equal to ma. Remember, you get full credit, or you get credit just for writing this equation down, so you might as well. And then we want to replace the forces in F equals ma with the actual forces in this problem. So let's write them out. The actual forces are the force of the scale and the force due to gravity. And according to Newton's second law, those two forces must equal ma. Now the force of the scale is upward, so we'll write that as being upward. The force due to gravity, as we learned earlier, is equal to mg, but g is negative, so that could be rewritten as m minus mg. And if we want to find the force of the scale, because remember that's the apparent weight, we would add mg to the other side, and we could factor out the mass, take the acceleration, add it to gravity, and have 85 kilograms times the acceleration, which is 2.0 meters per second squared, plus 9.8 meters per second squared. And that would give us a value of 1,003 newtons. Now, in part B of this question, it asks for the apparent weight when the elevator is moving at constant velocity between floors. So once again, we need to identify the system being accelerated. And again, it's the person. This is really important because it tells us what M and A are and F equals MA. Define the coordinate system. Upward again is positive. 3, identify forces by drawing a force or free body diagram and include the motion map. Again, motion map really important in this case. It says it's moving at a constant velocity between floors. We don't know if it's going up or going down, but as we're going to see in a minute, it really doesn't matter. So if the object is moving, or the elevator is moving with constant velocity, as it says in this problem, we know that the acceleration has to be 0. Because whenever the velocity is constant, the acceleration is 0. So our force diagram, which includes the force of the scale, has got to be equal to the force due to gravity of the person. Now this only happens when the acceleration is 0. So our next step is to explicitly write out the sum of the forces is equal to mass times acceleration. Write out what the forces actually are. The forces are the scale and the force due to gravity. We get these from the motion map. And we set that equal to the mass times acceleration, just like it says in our equation. However, what we notice is since the acceleration is equal to 0, I can set this just equal to 0, the entire Newton's second law equation, and I'll find that my scale, which again, since we said the force due to gravity is equal to mg, and because g is negative, I can just say that's negative mg is equal to 0. The force on the scale must equal mg. So that equals the mass, 85 kilograms, times acceleration due to gravity, negative 9. It's positive since we moved it over to the other side. When we moved this over to the other side, it became positive. And so this answer turns out to be 833 newtons. Okay, so we did step 5 earlier, and we plugged in all our values. Now for part C, it says what's the person's apparent weight when the elevator begins to slow at the top floor at 2 meters per second squared. So once again, we need to identify the system being accelerated. It's the person. To find the coordinate system, we'll say up is positive, down is negative. Identify the forces by drawing a force or free body diagram and include a motion map. So it says it begins to slow at the top floor. So it's moving up, but it's slowing down. Eventually it'll come to a stop. So that's what the motion map would look like. The acceleration arrows would point in the opposite direction. And that's really important because remember, the acceleration arrows tell us which force should be larger. So as we know, there's only 2 forces in this problem. There's a force due to gravity, and there's the force of the scale. So I'm going to draw the force of the scale on my motion map smaller than my force due to gravity, again because my acceleration is pointing downward, so my force due to gravity has to be larger than the force due to the force from the scale. Next, we want to explicitly write out Newton's second law so we can get that credit. Then replace the sum of the forces with the actual forces in our free body diagram. So let's do that here. Our actual forces are the force of the scale plus the force due to gravity equals MA, and then substitute the numeric values where appropriate and solve for unknowns. So the force of the scale plus the force due to gravity, remember we said that that's mg, and because a g has a negative value, we'll put that in as negative mg, and that equals the mass times acceleration. Now we need to be really careful when we do this problem, because notice the acceleration is downward. So let's remember that when we're plugging our value in for the acceleration. So again, we're going to solve for the force of the scale. That's going to equal the mass times acceleration plus mg, because I moved it over here. And that'll equal ma, so I'm going to plug in my value for my mass. My value for my mass is 85 kilograms. My acceleration, when I plug it in, this is where we got to remember that because the accelerations are pointed downward, the value of 2 meters per second squared must be plugged in as negative 2.0 meters per second squared plus 85 kilograms times 9.8. And we're putting this in as a positive 9.8. Again, the reason it's a positive 9.8, we have to be careful. It was originally negative when we were doing this problem. It was originally negative, and then when we moved it over to the other side, that's where this change in sign occurred. Okay, so you need to keep track of your values. So the force of the scale, or the apparent weight, is 663 kilograms.